welcome back. We're going to start our 9 o'clock session, and I'm extremely pleased to introduce you to a renowned researcher, if I may say so, in the area of in-memory computing, or his title of his talk is Memory-Centric Computing, and this is Professor Onur Mutlu. And let me tell you a little bit about him. He's a professor of computer science at ETH in Zurich. He's also right now visiting us. He's visiting at Stanford, and he's a faculty member at Carnegie Mellon University. So he's a faculty member at Carnegie Mellon University, where he previously held the Strecker early career professorship. His current and broader research interests are in computer architecture, systems, hardware security, and bioinformatics. He obtained his PhD and MS in ECE from the University of Texas at Austin, and the BS degrees in engineering and psychology from the University of Michigan, Ann Arbor. And he started the computer architecture group at Microsoft Research during 2006 and 2009. And he held various product and research positions at Intel Corporation, Advanced Micro Devices, VMware, Google, and he's received various honors for his research. Yeah. The list is quite long, but you have to trust me. He's received a number of Best Paper Awards, and he's most well known in the world in the area of memory computing. And he's going to tell us a little bit about this, right?
Thank you. Thank you very much, Sarma, for the nice introduction. I think I will need to use this one, right? So that I'm heard in the back?
Yeah.
Okay.
And that works? Okay.
Okay, this works, yeah. Okay, it's a pleasure to be here. As I said, it was a short drive, and I'll be here in the morning, and then I'm flying out, so I'd be happy to chat with anyone until I leave. I'm going to talk about memory-centric computing, in-memory computing, processing in memory. All of these are the same word, in my opinion, but maybe memory-centric computing encompasses them more. I have a lot to say in this topic, but I'm going to limit myself because we could talk days and days about this. I'll hopefully give you a summary, but feel free to ask questions and stop me. So today, computing is bottlenecked by data. There's no question that important applications are all limited by how fast and how efficiently they can access data. Machine learning, genomics, database, etc. Important workloads are all data intensive. They require rapid and efficient processing of large amounts of data. And on top of this, data is increasing. And what we want to do on the data is also becoming more sophisticated. And you can see this clearly with announcements that are coming out with ChatGPT or whatever they call it these days, right? There are many of these. I think they are just examples of machine learning. And in the end, we haven't figured out the efficient algorithms to do this learning yet. Probably it'll take us a while to figure that out. While we figure that out, the compute requirements are going to grow and memory requirements are going to grow, as you can see in this picture. This is a picture that I borrow from Cerebras' CTO. They're building these wafer scale chips to tackle this problem. Even with wafer scale chips, I think you don't have enough memory and compute coupled together because of the density issues we are having with SRAM. So machine learning is one example, but there are other examples like bioinformatics. It's an area we work on quite a bit. Today, we have data generators that look like this. It's a nanopore sequencing device from about 10 years ago. You can buy it for very cheap. And it has enabled the cost of sequencing to be much, much lower than the cost of a transistor today. So basically, we can generate a lot more data at much lower cost than we can put transistors on a chip. This means that we cannot really keep scaling up our transistors to analyze every single data point that we generate. Okay, so I can keep going with applications and studies, but I'd like to get to the point quickly. In my opinion, we have an even bigger responsibility going into the future, and that's sustainability and energy. Do we want to live in a world that looks like this, or do we want to live in a world that we cannot breathe in? I'd prefer to choose the first one. But I think I'd like to have the productivity with which we can actually solve problems. So I think we're very greedy as human beings. We want high performance, energy efficiency, and sustainability all at the same time. So how are we doing in our data design principles in terms of these three things, let's say? I think we're not doing well. Basically, we're accessing data, and data access is really a major performance energy bottleneck. And our current design principles are really exacerbate this bottleneck. Essentially, we move data between the processor and memory, or processor and the storage, and processor and network, wherever your data is, processor and the sensors. And your processor can be your favorite processor. It doesn't have to be a CPU. It could be the heterogeneous processors that we have today. We're causing great energy waste when we're moving the data. And we're also causing great performance loss. I put this in parentheses because we care a lot about this. Maybe we care less so about the energy waste, unfortunately. But because we care a lot about the performance loss, and we cared a lot about that for a long time, we put a lot of mechanisms in our systems to overcome that performance loss. We've built a lot of cache hierarchies, huge cache hierarchies, a lot of prefetchers in the system, sophisticated out-of-order execution, sophisticated multi-threading mechanisms. They all add to the hardware and software costs. And we don't normally add that as the cost, right? But they all add to our costs. When they work okay, usually. But many times they don't work in large data sets. As a result, they actually exacerbate both the performance loss as well as the energy waste. So we're in this vicious cycle right now. We keep on wasting energy without even thinking about it, in my opinion. And people complain about the AI training energy, right? So the main problem, in my opinion, is we're basically processing data far away from the data. And we built computing systems like that for a long time. Essentially, today's computing systems are all processor-centric. If you look at the fundamentals of computing, you need to have a computing unit, communication units, and storage and memory units. And if you look at it, you heavily optimize this computing unit and essentially left everything else dumb, meaning they cannot do anything to the data. If you want to do something to the data, you have to bring it to the computing unit, which is usually much far away from those other units. Okay, let me now give you some real examples. I've been talking, right? Anyone could talk, but this is actually a proposal that I had written to NSF when I was at Carnegie Mellon, my first proposal. And this was the picture I used. We were working on quality of service and multi-core systems, etc., predictability. Basically, we said that memory system is a large bottleneck, and this was the picture that we used. Essentially, if you look at this picture, computation is done only in the cores, the red parts. And your core can be your favorite logic, essentially. It could be a machine learning accelerator. Everything else is dedicated to storing and moving data. Caches interconnect, other caches, other interconnects, other caches, memory controllers, other interconnects, and storage. And most of the systems essentially dedicated to storing and moving data. If you do the calculations, more than 95% of a single node. That could go up to even larger, actually. And if you look at the core itself, that's a lot of SRAM, by the way. If you show this picture to a 10-year-old and say, okay, I'm building these systems, and most of my resources are dedicated to actually memory and storage. I should not have that problem, right? But unfortunately, our systems are still bottlenecked by memory. That means we're probably doing something wrong. We're violating some fundamental system balance design issues. I teach digital design to freshmen at ETH, and I used to do that at CME also. And one of the fundamental principles is balanced design. Right? You got to balance your design. And I'm ashamed to actually say, teach them later the processor-centric design that we have, which is essentially violating that principle from the get-go. We have no balance between memory and processor. Okay, so you don't like my picture. This is AMD. Nothing against AMD. They're building great processors. But that green box over there is L2 and L3 caches. And then there's a huge memory interconnect over here, as you can see. And we're adding more caches. Beautiful technology, 3D stacking. We should do it, but should we use it as cache? If you don't like AMD, here's IBM. Essentially the same thing. I could keep going on. I'll pick on Apple, who may not be here today. But essentially, if you look at the processor or chiplets, there are a lot of SRAM, essentially. And then there's DRAM, and there's a darkness that nobody thinks about, storage, which we should think more and more about and probably push processing a lot more into the storage system, which is essentially a system by itself today. Yet we're treating it as a dumb thing that just supplies data, right? Okay, so I think I made my point. I'm going to put some numbers to this also. Essentially, today, data overwhelms modern machines. Our storage capability, communication capability, and computation capability. And we're building powerful machines. We have not built this powerful machines at any time in the past. They're extremely good at computation. Computation is not a big problem today, in my opinion. Unfortunately, we're starving them. They cannot compute on things, at least to the capability that they're able to. Data also greatly impacts robustness, energy, performance, and costs. I'll briefly mention that. Let me give you some data on how bad data is. And I'll quote Dick Seitz. Probably there are a lot of people who know about Dick Seitz here. He was the chief architect of the alpha processors in the 1990s. And his team designed a flagship alpha processor in and after that, he wrote this one-page article. In this one-page article, he said that we designed one of the fastest processors of its time. It's capable of finishing 4 instructions, alpha instructions, every clock cycle. Unfortunately, on this important database workload that we think we designed this machine for, it's finishing only 1 instruction about 4.7 cycles, meaning it's operating at 5% of its efficiency. Clearly, there's a reason, and the reason is basically it's waiting for data to come back from memory. And he finishes the article with this sentence, I'm going to quote, I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Now, if you think about it, it's a 5% efficiency. We also are coming from engineering disciplines, right? What systems do we design that operate at 5% efficiency? Not so good. This system is designed to finish instructions, but it's not. Okay, so this is my own PhD thesis. We worked with Intel. We figured out essentially a mechanism to tolerate long latencies. We essentially looked at all of the workloads that they were using to design their processors with. And we found out that most of the time the processor is waiting for data. So this is very well known. You don't like the sites, you don't like me. Everybody likes Google. So Google published this beautiful paper in 2015 at ISCA, where they show that according to them, this is all of their data center workloads at the time, and top of the line processor at the time. It's finishing instructions. Basically, most of the time it's spending waiting for data. It's stalled by backend, and those backend stalls are mostly due to memory. Essentially, it's finishing instructions only 10 to 20% of the time. So the efficiency of that processor is about 10 to 20% across all of those workloads. Okay, so I think I made my point over here also. Essentially, we have a huge data access bottleneck, and we have not talked about energy yet. Now let's talk about energy, which is much worse than what I've shown so far. Essentially today, data moment energy dominates compute. And I'm going to use numbers from Bill Daly. These are old numbers. You can take a lot of issues with it, but the conclusion remains. And according to him, again, in 2015, this is the cost, energy cost of a 64-bit double precision floating point operation, 20 picojoules. And this is the energy cost of a main memory access, 16 nanojoules. That's 800x. Now, you may find 800x large today, I agree, but it's more than 2 orders of magnitude today, maybe 160x, maybe 150x. If you're lucky, 99x. Okay. And that is a complex operation. If you look at a simpler arithmetic operation, a 32-bit add, which no one wants to do today also, because everybody wants to do 4-bit or 8-bit or even 1-bit if they're capable of doing it. But let's look at a 32-bit add. The disparity, energy disparity between a 32-bit add and a DRAM access is 6400x. And if you go to storage, it's not even storage. If you go to storage, add another multiplier over there, at least 10x. So the question is, do we really want to move data? If we keep moving data like this, we're spending energy. These are some works that we did with Google. We looked at mobile workloads like YouTube, etc., or Chrome, and also TensorFlow at the time. And we found out that more than 60% of the total system energy in those workloads are actually spent on data movement between the processor and the memory. And these are not the most intensive workloads. If you look at more intensive workloads, we also studied a state-of-the-art edge machine learning accelerator at Google, and using their own machine learning models. And in large machine learning models, more than 90% of the total system energy is spent on memory, essentially. In many cases, 99%, 99.8%, etc. Those numbers are actually real. Okay, basically, I think we do not want to move data today. We need a paradigm shift to enable computation with minimal data movement. We want to compute where it makes sense, where data resides. And there are many places where it may make sense. Sometimes the processor makes sense. Sometimes the GPU makes sense. Sometimes the sensor makes sense. Sometimes the tape makes sense, if you're capable of doing that, of course, right? So we would like to enable at least those options to do that. And this is enabling computer architectures to be more data-centric. And this is an example of where it may make sense, a limited set. Right? Storage, in my opinion, makes a lot of sense. But I'm going to talk a lot about DRAM today, since DRAM is a technology that's actually quite powerful. And we could actually do a lot with DRAM, but other technologies are also quite interesting. Okay, let me give you the high-level idea. This is not the most aggressive form of what I've been describing. The more aggressive form is essentially everything that can compute or that is potentially capable of designing as compute capable is an agent. And they're equal agents. They actually communicate and they complete a task as a distributed system. Clearly, we're much far away from that today, right? We are still very CPU-centric. To a more adaptable path is you still start tasks in the CPU, and the CPU offloads some tasks to memory or storage. And today we actually store a lot of our data in memory and storage. A lot of applications fit memory sizes of today. So the CPU asks the question to memory, can you do this function for me, or can you execute this application for me? Memory says yes and returns the results. Clearly, it's not as easy as that. There are a lot of things that need to be answered over here, right? How do we design the compute-capable memory? What are the mechanisms inside and the controllers? How do we design the processors and communication units in light of this? How do we design the software and hardware interfaces to enable this? How do we design the system software compilers and languages to actually make it more applicable to the masses, let's say? And then how do we actually take advantage of, or how do we rethink our algorithms to fit what's going on the memory side or the compute-capable device side? And then I think we also need to think about our theoretical foundations. So this is clearly a system stack problem. And you can actually innovate across the stack, all the way from devices to algorithms at any point. And there's been a lot of research. I'm going to show you some examples from a limited subset of the domain. But there's a lot going on. There's a lot exciting going on. And probably you'll see some examples from the students who've been doing some of the research over here. I will mention one thing, though. Processor-centric paradigm is so ingrained in our thinking. Everything we do. For example, if you actually have taken a theory of algorithms course or a computation theory course, you probably counted operations, right? The complexity of an algorithm is determined by how many operations it does. But maybe that's not important anymore in our systems, or not as important. So we don't essentially have a theory that's much more data-centric or memory-centric. And we need to develop that theory also. Okay, so let me also say that this is not a new idea. And this is an old idea. People have developed, they called it logic in memory in 1960s. If you know earlier papers, please let me know. This is an example of near memory processing. I'm going to define near memory versus using memory. And I'm going to look at a more aggressive form of processing in memory, which is using memory in this talk. But near memory processing is essentially you have some memory and you put logic next to it. So people have thought about this. And Harold Stone, who's been around here, has written papers about it also, as you can see. What is different today? Like, why should we try to make it happen today? In my opinion, we have nowhere else to escape. Basically, that's my answer to this question. Today is very different from 1960s and even 2000s, even 2010s, right? We didn't have ChatGPT, for example, in 2010, or even 2 years ago, let's say. So basically, we're having, but I think we're having problems not only at the application level and system level, but we're also having problems at the memory level, technology level. We're having a lot of problems with the memory technology. We've tried to replace DRAM with technologies that may or may not scale, and we're not sure if they scale, but at least they're not successful at this point. At least, but they may be successful at some point. The technology scaling issues are not going well, essentially. We have a lot of work on RowHammer that I'm not going to talk about in this talk. That's an exciting area that still goes on, for example. And these scaling issues actually demand intelligence in memory, in my opinion. Basically, if you want to solve these issues, you need to have an intelligent controller that is compute capable on the memory side. For example, if you look at the flash memory, NAND flash memory, which we have actually done a lot of work on also, you need to have an intelligent controller to make the memory work. And I think going forward with main memory technologies, we need to have those intelligent controllers. So if these intelligent controllers are already there, you could also use them for computation. And I've already given you the application and systems perspective. We have a huge demand from the application and system sides, and we need to really improve all metrics that we care about. So our designs are really squeezed in the middle today. We have nowhere to escape, in my opinion, unless we fundamentally find a new technology that is not bottlenecked by memory, which is very difficult to imagine, in my opinion. But we should try to imagine. I like the word ideas in the center. We need ideas going into the future. Okay, so that said, I think because of this squeezing, in my opinion, we're actually seeing a lot of effort in industry as well. If I was giving this talk 5 years ago, you would have seen some of these. We have 3D stacking technologies. You could put logic in the logic layer and do computation there. And Micron was experimenting with things. But the lower part of this picture was not there 5 years ago, let's say. We have startups like UpMem, who are putting actually processors inside the DRAM chips. And we actually played a lot with their designs. We looked at the bottlenecks, etc. I'm not going to talk about that. This is near memory processing, which is very interesting, but we don't have time. Samsung has been putting processors or machine learning accelerators next to DRAM banks. So does SK Hynix and Alibaba. And people are putting memory controllers on boards also. So the good news is I think we're taking steps in the right direction. The question is, can we actually amplify that a lot? And there are many other experimental chips and startups that are also happening. And I think their interfaces like CXL can also help, in my opinion. We need much more, let's say, flexible interfaces to do offloading to memory. CXL can help with this, even though it may not be the perfect interface. People have shown some results, as you can see over here. Okay, we have a lot more coverage in this large paper that we keep updating on archive. So if you want to really get an idea of what else is going on, I'd recommend you take a look at this paper. But I'm not going to talk about a lot of the other things than what I'm going to focus on next. And we also have processing in memory course, and we will hold a processing in memory tutorial at ISCA, which will be all live streamed. So if you're interested, you can attend remotely as well. Okay, now let me go into some example approaches that we can follow today, or maybe going to the future, not today necessarily, right? Sorry, I'd like to take some water over here. Feel free to ask a question in the meantime. Okay, no questions, so maybe I'll go through it. So essentially, I would like to first define some terminology. I've been saying processing near memory. What does that mean? I think, so there are fundamentally two types of processing in memory. One is near memory, the other is using memory. Near memory is what's happening today, and I think what's going to happen more easily. Using memory is much harder, but I believe in the end we need both to be fundamentally much more efficient. So what is near memory? Today you design logic, you design memory. They're designed completely separately, right? And near memory means that design logic as you design today, design memory as you design today, put logic closer and closer and closer and closer and closer to memory. Use 3D stacking technology, use 2D technology, whatever you use, put it into memory controllers, put it in the DRAM chips, put it in a board, but the logic gets closer to memory. That's near memory, which is not that different from what we do today in a sense, right? And I think we should do it. And there are a lot of challenges over there also. Some adoption challenges still exist over there. Using memory is fundamentally different. Using memory says, here's logic as you design today. Here's memory as you design today. Forget about logic. Now think about memory not as you design today, but think about it as a computation device. Every memory has analog operational properties that you can exploit that enables computation. And I'm going to talk about that from the perspective of DRAM. But this is true for NAND flash. This is true for RRAM. This is true for STT-MRAM, PCM, whatever memory. You can think of it as an analog computation device. And the good thing is some memories already have analog to digital, digital to analog converters, DRAM being a good example of that. And you can actually take advantage of those conversion capabilities internally as well. In the end, I think this is much harder because this is at the core of it, it's analog computation, but it gives you the higher benefits in the end. But there are some examples of this that's going to be easier. I will mention that also. In the end, I think we need to combine both to get the best of both worlds. Okay, so that was the nature. And then you can think about technology, which I'm not going to talk too much about. And then there's the location of where you want to do processing in memory. In the end, a processing in memory engine or type is a tuple of all of these three. And you can have essentially all combinations if you wish. Okay. So just to remind you, we're going to use memory as an accelerator. We're not going to do everything on the memory side. And I never suggest this. In the end, we need to exploit heterogeneous resources. But we want to enable computation capability over here. If you look at our computation capability, it's always on the left side on the memory bus. Nothing on the right side of the memory bus, right? But we want to do that. Okay, so I'm going to focus on processing using DRAM and main memory. Just to give you a quick insight, if you want to sleep after this, feel free. But basically, we can support a lot of things by modifying DRAM chips or even in off-the-shelf DRAM chips today by violating timing parameters. We can support bulk bitwise operations and or not a majority. Bulk bitwise copy, initialization, and zero. I'm going to start with that. True random number generation, physical unclonable functions. And if you want to modify more, you can do lookup table-based computation. And this is not changing a whole lot in DRAM except for the lookup table-based computation part. You can do most of these at low cost, and I'm going to talk about the basic ideas. Even in off-the-shelf commodity DRAM chips, we can do some of this, even though they're not supported, right? We get significant performance and energy improvements. So let's start simple. This is the thing that I think is more easier to adopt because data copy initialization is clearly a bottleneck in many applications, even though, again, this is not talked about. Many workload suites don't actually demonstrate it. But Google, in their paper that I mentioned earlier, showed that approximately 5% of the execution cycles in their data center is spent on two function calls, memmove and memcopy. This is a bit crazy in my opinion. Only two function calls occupying 5% of the cycles, right? Okay, so what do we do today? Essentially, if you want to copy, let's say, a 4 kilobyte page to another 4 kilobyte page in memory, white page to the gray page, you go through the processor, byte by byte, bring the source page and the destination page, write the data, and write back the destination page byte by byte. Clearly, this is high latency, high bandwidth utilization on perhaps the most important resource that we have today. We cause cache pollution, but you could eliminate that by doing DMA today, right? And you cause a lot of unwanted data movement, because imagine you're initializing a 10 terabyte database. You're not going to have locality in your caches to exploit in that database. And many works have shown that. And it's not just database, it's graph analytics, etc. also. So essentially, if you do a 4 kilobyte page copy via DMA today, it's about 1,000 nanoseconds and 3.6 microjoules. Now, again, let's think like a 10-year-old. Show this picture to a 10-year-old and ask the question, how should I do it? I'm going to experiment with this. But basically, I think they would say, oh, why don't you just do it in memory, right? That's what you're trying to do. So I think we should probably think about 10-year-old, and we should try to enable that thinking in real industry settings, as opposed to saying, oh, this is never going to work. Okay, so this is going to be low latency, low bandwidth utilization, no cache pollution, and no unwanted data movement. Essentially, I'm going to show you a mechanism that takes, without much optimization, this 1,000 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules. And the basic idea is very simple. And this is the most, let's say, this is the best you can do, in my opinion, currently, without changing much. If the source and destination rows are mapped to the same DRAM subarray, which you could also enable to do if you expose this to the higher levels of the system stack, you first activate the source row, which brings the data into the sense amplifiers, row buffer. Now the data is strong in the row buffer. And then you activate the destination row while deactivating the source row, which means that you connect the row buffer to the destination row. And the row buffer sense amplifiers drive the data that they captured from the source row into the destination row. And that's the idea, basically. 2 consecutive activations. Negligible hardware cost. In fact, almost no hardware cost if you don't need to determine whether you're in the same subarray or not. And if you actually violate the timing parameters, this is doable with 99.99% reliability in existing DRAM chips. I'm going to talk about that. So we're almost there, basically, in this. It already exists. We don't have the interfaces to take advantage of it, but chips are already capable of doing this with very high reliability. Okay. So what is the benefit? Essentially, you reduce the latency of a 4 kilobyte copy by more than an order of magnitude, and the memory energy by between 1 to 2 orders of magnitude. So we've published this idea. Later work actually used some of the infrastructure that we developed to violate the timing parameters and show that existing DRAMs are actually capable of doing this. We built on these folks' works that showed that you can actually design FPGA-based infrastructure that does this on real applications. But I'm not suggesting you should do this for real applications, but this is a prototype that we developed. What this does is you can run an application on the RISC-V system that's on the FPGA board. And whenever you get a copy request, page copy request, we modify the FPGA and the memory controller such that that page copy request gets shipped to the memory controller, which violates the timing parameters to actually do the copy in memory. And of course, to be able to do that, you need to change the operating system to support the mapping mechanisms, data mapping mechanisms, and the paper talks about that. We also actually enable random function calls to be shipped to the memory controller such that the memory controller violates the timing and generates random numbers in DRAM. I'm going to talk about that very briefly. So you could actually do this. You could build this infrastructure, and I welcome you to test it on your own. You could download it. It's all open source, and we'd be happy to support it if people need help. And you could actually get results. Because the microcontroller is actually very weak, it's about 50 megahertz or so, the effect of initialization and copy is actually much larger. So you actually get much better benefits. You don't see this high benefits on a 4 gigahertz processor. Okay, so this is a paper you can take a look at. So you can ask a lot of questions. Data mapping is important. Yes, you need to change the data mapping. It's not that bad for this purpose. It's going to get worse for other purposes. You could do this across banks. It's actually existing DRAM chips have mechanisms to transfer data between banks. You just need to modify the DRAM to enable this. You cannot do it on off-the-shelf DRAM chips, as far as we know. You could move data at smaller granularities by modifying the DRAM a little bit. You could do interbank copies at the lower layer, at the logic layer, if you have a 3D stacking. But these are not computations, so maybe I'm boring some people over here. What about computation? I'll flash these papers that I mentioned. So essentially, you can also do computation. Let's talk about computation now. Let's talk about simple computation. To begin with, more complicated computation, we need to talk in more detail. Essentially, we're going to introduce a primitive, multiple row activation. It's doable in DRAM. It's doable in other memory technologies also. I'm not going to talk about other memory technologies, except I'm going to flash a slide later on. Probably there'll be discussions about other memory technologies, which are quite interesting in my opinion. Okay, what is multiple row activation? In particular, triple row activation. you have 3 rows, A, B, C, in DRAM, and you see the capacitor over here and the access transistors. I'm showing you only one bit line and one sense amplifier over here. If you concurrently activate these 3 rows, what you get is a bitwise majority function based on circuit principles, right? Essentially, if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. So bitwise majority is beautiful. If you read Donald Knuth's 4th book, he talks about it a lot, actually. You could rethink your algorithms to take advantage of bitwise majority. Bitwise majority is also nice because you could take out C. If C is set to 1, you get the OR. If C is set to 0, you got the AND. What is missing is NOT, clearly, right, to be functionally complete. And to be functionally or Boolean complete, you could actually get the NOT with some modification. And the idea is if you activate one row, you get the value of the capacitor over here and the complement over here, right, on the other side of the sense amplifier. You just need to feed it somewhere. Now, where do you feed it is a question that I think is going on, but we fed it into the subarray with some modification to the circuitry. It could be expensive in more recent technologies, but there are other ways of doing this also. Now, if you do this, essentially what you have is a functionally complete bulk bitwise computation engine in DRAM. It's essentially capable of doing anything. You just need to rethink your algorithms to take advantage of it. And some algorithms are already capable of doing it. For example, people have been building databases with huge bitmap indices. They do huge bulk bitwise ORs and ANDs. Not even NOTs sometimes. ORs and ANDs are there. XORs also, which is ORs and ANDs and NOTs essentially. People have been designing databases for that purpose, web search engines, etc. I'm going to give you an example from one database very quickly. Essentially, we ported this bit-weaving database that was developed at the University of Wisconsin to our simulators, and we find essentially you get significant performance improvements and energy improvements by taking advantage of this bulk bitwise computation engine. Clearly, you need to do a lot of work as a programmer to do this mapping, right? But you don't need to rethink your algorithm a lot, at least in this particular case. Okay, there's more in the papers. I'm not going to talk about these in detail. So how do you, then the question becomes, there are multiple questions after this, right? What other operations can you do? I'm going to leave that for later. How do you make this more programmable? How do you make it easy for the programmer to take advantage of it? And this is one way of doing that. We introduced a SIMD framework. Essentially, what we have is a bulk bitwise SIMD engine. So we need to target our design or programming to take advantage of this bulk bitwise SIMD engine. And this is one way of doing it. Essentially, we have the programmer specify a desired operation. This desired operation could be as simple as an addition, or more complicated like an FFT, or or like a convolution or matrix multiplication. And you could specify all of those as circuits, right? Probably a lot of you are circuit designers here. You could write a circuit that looks like this and or not gates. We basically do a majority inverter graph on top of this. We use some of the quantum computing electronic design automation tools that were developed by EPFL to minimize that graph. And we basically map it later to a sequence of DRAM commands that include triple row activation, row clone, row copy, and also some allocation of rows inside the DRAM. I didn't go into a lot of detail on how we actually implement this, but I'd be happy to. Essentially, you have a micro program that implements the circuit that you specify. And that circuit can do anything, essentially. And we associate it with an instruction. When that instruction is used in a program, the processor ships that instruction to the memory controller, and the memory controller fetches that microprogram and executes that microprogram on the memory side. So this is one way of actually implementing anything on the memory side using a single instruction or instructions added to the ISA. And these could be customizable instructions also, if your ISA actually allows that, right? Some ISAs actually allow that. And if we want more of that going into the future. Okay, there are a lot of details that I skip over. I'd be happy to talk about that. But in the end, if you do this, you get significant performance benefits over an existing CPU and high-end GPU also, and energy benefits also. So you basically improve both performance and energy. Okay, there's more on this. So more recently, actually, we've been trying to overcome some of the downsides of SIMD. One of the issues is when you actually do a SIMD, you need very large vectors because the row size of existing DRAMs is 8 kilobytes or 16 kilobytes. If you actually aggregate a lot of things, right, in a DIMM, in a module. Internally, in a bank, it's actually smaller. But in the end, we want something much smaller because not all programs have those large vectors. And that's what we introduced over here. I'm not going to go through this in detail, but in this work, we target that. We actually changed the DRAM to use more bit line segmentation, word line segmentation, so that you can actually do this operation in individual mats separately. And we also add compiler support to do this and limited interconnect support, which I'm going to get to probably later on. But one of the issues, if you want to do computation on the memory side, you cannot design memory as memory. You need interconnect over there. Because if you cannot communicate between different banks, then you have a problem. Right? So this enables communication between bit lines. Again, I'm not going to go through this, but we have some compiler support that you can download online. And we see significant benefits with this MIM-DRAM that makes the programming much more flexible. Okay, as I said, you can actually, if you want to implement much more sophisticated operations, for example, a 64-bit multiplication, this is not your substrate because it's a bit serial, bulk bitwise substrate. You're actually taking advantage of the large amount of parallelism in the bit lines to overcome the latency of a single addition or multiplication, right? For 4-bit multiplication, you're okay. For 64 bits, this doesn't scale very well. It scales quadratically, actually. So if you want to do things like that, you need lookup tables. Well, if you want to do that using memory or computation logic, of course, that you add, which is probably costly. But if you do lookup tables, you can do a lot more computation, as we've shown. I'm not going to go through this in detail either. So what else can you do on the memory side? Essentially, we've abused timing parameters on DRAM chips. Oh, I should also say that before going that, I forgot. This triple row activation, we asked the question, can you do this in real DRAM chips? And the answer is yes. I'm going to get to that. Essentially, with some DRAM chips, if you violate the timing parameters carefully, you get a bitwise majority function. And you see that bitwise majority function. It's beautiful. I'm going to get to that in a little bit also. What else can you do in DRAM chips? If you violate the timing parameters, because you don't have anything else to do, right? We don't have programmability in the DRAM controller at all. The best we can do as researchers is to violate the timing parameter to see what existing commercial off-the-shelf DRAM chips are capable of. We did that with a lot of LPDDR and DDR chips. And essentially, we showed that if you violate the latency parameter, activation latency, some cells randomly fail. Meaning in one access they fail, in another access they don't fail. So it gives you a bit string of random numbers. Essentially, you can generate random numbers in DRAM quite reliable. And this paper discusses that. This also spun off some work that showed that you can actually do even better random number generators in DRAM by violating more timing parameters, like doing 4-row activation, etc. Okay, so this is, I think, interesting. Random numbers are interesting because in the end, if you want to do a computation on the memory side, you need a security substrate over there. And you need random number generators for that. And I believe, actually, more memory-centric computers are also better for security because they reduce the data movement. One of the issues we're having with security today is you're moving data all around. As a result, you're exposing them to a lot of side channels. If you keep it in one place, and if you actually have security substrate around that place, you can actually, in my opinion, be much more secure. Okay, so what else can you do in DRAM chips? We keep asking this question. In this more recent work that was presented at HPCA, we showed that you could do a lot of interesting things. You could, maybe I go to the next slide as opposed to reading the abstract. Essentially, we were able to simultaneously activate up to 48 rows in 2 neighboring subarrays by violating the timing parameters. And there's a reason for this. This is because of the row decoder, hierarchical row decoder design. If you don't give the row decoder to actually settle, a lot of word lines become active. And this enables a lot of word lines to actually connect to, and other cells to connect to the bit lines. And as a result, you get a large majority function, right? 48 input majority function. Now, if you actually, we also showed that you could actually do the NOT operation in existing DRAM chips, which is very interesting. I'll leave you to the paper, or I'll be happy to talk about that. You could also do AND, NAND, or and NOR operations that are 16 input. Again, we're not modifying anything in DRAM, just the memory controller violating the timing parameters. I think this is fascinating. And you can see the reliability. Reliability is not as large as copying data because these are quite sensitive to noise that's happening. And the DRAM chip is clearly not designed to support this. The fact that we're able to get this is, I think, fascinating to begin with. Okay, I'll not go into this because we probably don't have a lot of time. I'd like to leave some time for questions. Yes, please. Oh, how do you violate? That's a great question. So we use an FPGA-based memory controller. Probably I should have copied that picture over here. We've been designing FPGA-based soft memory controllers for a while for many reasons to test DRAM. And we can violate any timing parameter in that controller. That said, I think some commercial chips have memory controllers that are configurable if you know that configurability parameters. So you could actually do this in commercial chips also. Maybe not to the extent we could do it. Okay. Okay, so as I said, these ideas are all applicable to other technologies as well. I'll very quickly cover flash. This is a recent work that we've done on real flash chips. Essentially, the idea is very similar. If you activate multiple pages in the same block in flash, you enable simultaneous sensing of those pages, and you, in this particular case, you get a 32 input bitwise AND. And the reason is, again, the way Flash operates. If a bit line over here reads as 1, when all of the target cells store as 1, store 1. Otherwise, the bit line is inhibited, right? So you get a 0 in the end. This is intra-block, within the same block. If you activate different pages in different blocks, you get the OR function, bitwise OR function, and there's a reason for that also. And in Flash, we're actually even better because NOT already exists. You could actually do NAND, XOR, and XOR. So you actually have a block bitwise computation substrate in Flash also. In this case, we actually did a lot of real device characterization using real Flash chips, and we saw this in real systems. You get a little bit latency increase to do these operations, but not too much. And in Flash, because you have an intelligent controller, you could actually adapt the reliability of that controller. What we do is we actually change the programming level so that you don't get bit flips or errors in this computation. In DRAM, we don't have that luxury, unfortunately, because our controllers do not know about the device. And also, it's difficult to control the capacitor charge compared to the floating gate rate. Okay, so these are some real results from application. Again, simulated based on what we saw in real chips. You get significant performance energy improvements. Okay, you can do similar things in non-volatile memories. There have been other papers that are published. And you can also do other things in non-volatile memories that are quite exciting, in my opinion, which is matrix vector multiplication in the analog domain. And I'll leave you to these papers to think about. Now, since we don't have time, we're not going to discuss processing near memory, but there's a lot of exciting things over there as well. And I'll leave that to the paper. Let me mention some things, though. I think you can build any hardware you want in the end. It's costly, yes. But we need to think about adoption. And I think there are a lot of potential issues in adoption. Applications and software. Most of these are software and system level issues. Building hardware is good because it enables adoption of some of these issues, right? For example, in my opinion, if people build the idea of row clone, software will be written to take advantage of it. It will take some time. Nobody is going to write software for simulators. And this has been proven for a long time, basically. So if you demonstrate something in real hardware, people are going to write software for it. Okay, but there's ease of programming, that's important. The system and security support, that's important. Runtime and compilation support, and infrastructures. In my opinion, all of these are doable and solvable, and there's research that's going on. I believe the research should be even more intensive in all of these areas. But the biggest limiter that I see, not only in industry, but also in academia sometimes, is the mindset. This processor-centric mindset is so ingrained in our thinking and education, is that whenever you propose some change to the system, they say, oh, but it doesn't work with this. Oh, but it doesn't work with this data mapping mechanism that I have. Oh, the processors are not designed that way. Yes, absolutely. All of those are true. Because we're not designing a system to work with everything else that has been introduced in a processor-centric system, right? So I think we need to change our mindset to be more open and enabling. Otherwise, this will never be enabled, in my opinion. This will be yet another, what I've shown you here in 2024 would be yet another paper that someone else maybe discusses in 2064, saying that, oh, people have thought about this idea in 2020s. I don't want that to happen, but yeah. Essentially, we need to revisit the entire stack. Okay, so let me conclude. I think the reason we don't want that to happen is we're having a lot of issues, right, with energy. And if you want to be fundamentally energy efficient, we want to be memory-centric or data-centric. If you want to be fundamentally high performance, we want to be data-centric also again. I believe, but I'm not going to write that on the slide. If you want to be fundamentally secure, you also want to be data-centric today. This is something we're working on right now. That's something interesting too. We now want to minimize data moments. Okay. I think if we don't have, do we have time, Sarma? Okay. Let me quickly conclude then. Basically, this is part of a larger agenda. I think we need to be memory-centric, but also we need to be more data-driven and data-aware. If you want to know more about this, I'd be happy to talk about that. But all of these, I think, require enabling computation capable inside and close to memory. This can lead to orders of magnitude improvements. I've shown you some examples today, but also near memory computing that I didn't want to dismiss it, but that's more shorter term. Even with near memory computing, we see orders of magnitude improvements on applications like graph analytics, for example, or machine learning. We can enable new applications and computing platforms this way. I believe in genomics, for example, there's a huge opportunity here. This also can enable a better understanding of nature. Sarma mentioned that I have a psychology degree. When I was studying psychology, I was also studying computer science engineering at the same time. And the psychology textbooks were written saying that oh, we can explain how human brains work by using the computer as a paradigm. Psychologists abandon that quickly. If you look at the modern textbooks, they don't talk about that because they figured out that a modern computer has nothing to do with a human brain. But a human brain does perhaps things in a more memory-centric or data-centric way. So I think the future is bright, but we need to change our mindset and do research and design across the computing stack. I'll leave you with this picture before acknowledgements. But if you look at this, what I believe is a device that does some computation, it doesn't do the computation the way we have designed our systems today. It essentially, well, I don't know everything about this clearly, and I don't believe anyone knows everything about this, but it seems a lot more memory-centric, where memory, communication, and computation are closely coupled with each other in some way that we don't quite understand. That's why I think we need to revisit the entire stack. Okay. All of these things that I mentioned are online on papers and source code. We release a lot of source code, and I'll acknowledge my group also to who have done a lot of this work. I'd be happy to take questions. Thank you.
Yeah, very interesting ideas and research. For memories to be usable in the real world, they need to be testable and also repairable in many cases. So I see, and they have some of the operations you shared with us today are quite complex in terms of all the things that need to work in the hardware and other things to work. So have you given thought to testing those functions and the repairability?
Yeah. I mean, that's a great question, certainly. So I think what we have done is not exactly I have described. We've given a lot of thought into this. So you don't actually design all of the memory to be capable. What we do is, for example, you have a DRAM subarray. You cannot do a triple row activation on arbitrary rows. We actually allocate a small portion of the subarray to be computation capable. If you want to compute on rows, you need to move the data from the data part of the subarray to the computation part of the subarray. And now you design the computation part to be much more reliable because your row decoder is much small. You need to keep this variation in check, and you need to add error correction, etc. So that's one direction, but there needs to be more work in that direction. Clearly, that requires a lot of design and reliability testing. But we have another direction where we do a lot of testing on memory chips also. Yeah.
So, earlier on, by the way, very interesting talk. Thank you very much.
Thank you.
So this is very, very good. So earlier on, in a slide, you mentioned heterogeneous compute, right? Fundamentally, this is sort of, it is really looking at the problem as a heterogeneous compute problem. Now, one of the biggest challenges of heterogeneous compute is the programming model, right? That's where, we are Qualcomm, we have a lot of processors on our handsets. We have a CPU, GPU, NSP, you name it, right? But yet, it's not a uniform programming model where the user doesn't need to be aware of what's inside a processor. So how do you see that challenge being addressed in the context of processing and memory?
Yeah. I mean, that's definitely one of the adoption challenges, basically. How do you enable programming? So I think we need to do more research in it. So what I've shown you, offloading as a instruction is one potential programming model, but that cannot be the only one, because there are some other models where you actually expose the processing in memory engine and users can directly program it. You get a lot more benefits if you actually do things like that. So in my opinion, I don't have an answer, essentially. How do I see challenge being addressed? I think we need more research. People should be developing more programming models. They should be trying it out, both in simulation as well as real hardware, hopefully. And we have been doing that in our results. Some of the programming models could be inspired by distributed systems frameworks, especially if you're doing near memory processing. You can ship computation to where the data is using remote function calls, for example. We propose those programming models for near memory processing engines. But I don't know if there's the best programming model currently. What we're working on right now is taking advantage of some of the features that are there for CUDA, for example, and targeting them for processing in memory engines because people are already programming a lot in CUDA. for better or worse. So I think it needs to be explored. I don't have a perfect answer. Thank you. Yes. Oh, okay. Maybe maybe the microphone needs to go to the.
Yeah. Well, yeah.
Yeah.
So it seems to me that the way that we build complex chips and then we validate them, it takes like up to a year to validate and ship a new chip. It's very complicated. And a lot of it has to do with how you validate it, and the validation sort of takes place at different levels of abstraction in the system. And it seems like by processing in memory, you're basically breaking through the barriers of those abstraction layers in some ways. So have you given any thought to that, and how might that work?
Yeah, I mean, I think that your question has synergies with Fadi's question earlier, in my opinion. I think, I mean, we need to do validation. We need to perhaps do different validation, but I'm not sure if it really fundamentally changes anything we do, right? We still need to validate the hardware we design, right? If you're thinking about analog validation, yes, I agree. At least the part that I talked about, the analog validation, we need to develop the tools for that, right? But there's the near memory part that I did not talk about that could use existing validation tools seamlessly. Does that make sense? Yeah.
Thank you very much for the very insightful talk. And the idea of using a memory device existing for doing various computation was mind blowing. And I was imagining like how this work in multi-core architecture. So I was imagining maybe there might be consistency issues if the data is copied to multiple processors. And so I have two questions. One is how do you deal with this consistent problem when you use the memory for processing? And was there any overhead caused by consistent handling?
Yeah, certainly. I mean, that's one of the system issues like coherence, right? And even if you don't have multiprocessors, even if you have a single processor, which we don't have, you still have a consistency problem or coherence problem with the caches, right? In the end, if you're going to do this computation, you need to look at a coherence model. And we've explored some of those coherence models in prior work. Do you support fine-grained coherence, coarse-grained coherence? Do you expose it to the programmer? All of these are important issues. In some of these works, we basically tackle the problem by saying that, oh, if you're doing operations, if you're doing offloading of computation or data copy through DMA, you need to do something like that anyway today. So you can take that simple option. But if you actually add more coherence support, that's aware of this near data processing or processing in memory, you get even higher benefits. You have some papers. But there needs to be more work in that area to make things more efficient.
Just following up on that question.
Sure.
If you take your memory, your DRAM, and you put logic either on the same die, wherever you put it, and you encapsulate that with a proper abstraction in terms of an instruction, so this is just another processing unit, right? Which has some, instead of SRAM, you now have a very large capacity DRAM. Why does coherence become an issue? Or why does it become a new issue?
Yeah, I agree. I think another way of answering is the question could have been, you actually have today heterogeneous processors and you still have the same issue, right? You need to satisfy coherence when you offload computation somewhere. But near memory, I think, is a little bit different. It's not a new issue. It changes the issue a little bit because you're trying to avoid computation, and this coherence actually can cause a lot of you're trying to avoid communication, and this coherence can actually overcome what you're trying to avoid by causing a lot of communication if you don't have the right coherence model. Yes.
Excellent talk, by the way.
Thank you.
Computing. So my question is, has it made it into any practical situation, maybe some mixed space like IoT or some space like that, maybe?
Yeah, I mean, not that I'm aware of. Let me see. I have this picture. People have been building chips, clearly, more prototypes. I think Samsung, people can speak for themselves. Alibaba and SK Hynix, they've been doing this to accelerate machine learning workload. They actually have floating point multipliers inside the DRAM. I don't know if they're being used anywhere. UpMem is something you can buy. I don't know if people are using it. We've shown actually some workloads actually benefit a lot. Not all workloads benefit. It's a much more general purpose engine. And then there's a lot of experimental startups. And I don't know their current outlook. Yeah. IoT could be a place actually where you could do a lot of this processing nicely, but again, I don't know the answer.
Okay, we have lots more questions. I have more questions, but we're sort of coming
Sure.
to the end of the session because we have a online session the next week.
Our speaker's dialing. You guys can continue talking. I just need to get that call set up.
Yeah.
Okay.
You guys can keep talking if you don't mind.
Thank you.
Do you have any questions with everyone?
Okay, please go ahead.
What problem that comes up with is like not see right?
Yeah.
It's up, then you have a problem.
Yeah.
So what's the state of the art in that area, with like doing ECC or some kind of correction of this while you are doing film on them?
Yeah, that's a nice question, and that's definitely a problem. And people have been writing papers about it. There are some papers that I can point you to. So you need to do correction while computation, essentially. So you cannot just do correction outside the chip, right?
Yeah.
Or even inside the chip, the way we're doing it today.
It's like the sensing HBM style, you could do it. It's reading out.
Yeah. You mean processing near memory, right? Yeah. Sure.
Using memory is more tricky. Right?
Exactly. Yeah. Because fundamentally, you're operating in analog mode, and you need to do error correction while doing computation, or you need to do some checking. So I think there's a good space over there that's not even being examined as much as it should, right? And actually, I think this is actually a really interesting space for information theory people as well. Right? Yes. Oh, maybe I should use that.
Does this idea of near memory computing eliminate the idea of cache by any chance?
So that's a great question. And the short answer is no. Meaning locality in programs are so strong that whenever we wanted to examine that question, we always had to put some caching or buffering on the memory side. The caches are not as big. They're smaller, but you need some locality. So that's one. And the other reason is the latencies that you have, at least in existing memory technologies, are long, right? So you still want to tolerate some of those latencies if you're doing near memory computation.
And when it comes to near memory computation again, so would this sort of cause an increase in the hierarchy as well? Because now the memory is sort of more complex in its way. So are we sort of increasing the hierarchy again?
I guess maybe this is coupled with your previous question. So yes, you can think of it as potentially increasing the hierarchy, but you could eliminate some of the other cache on the CPU side. So I think I answered your question assuming that can you eliminate on the memory side? So on the memory side, you don't need that big caches, but you still need some caches. But now that you have some computation offload to the memory side, maybe you could eliminate a lot of the large caches, huge caches on the CPU side.
I'll have to stop the Q&A.
Okay.
Thank you very much again.
Thank you. So thanks for the questions.